In this lecture, we will be reviewing the concept of air pressure and connecting air pressure to the presence or absence of wind. At the end of this lecture, you should be able to define air pressure, summarize the difference between high and low pressure systems and associated wind directions, recognize the difference between high pressure ridges and low pressure troughs, and begin to combine this knowledge to understand weather maps. Information from this lecture will prepare you to complete the air pressure and wind exercises. Let's start out with a review of air pressure, which we covered in Chapter 2 of JetStream. Atmospheric pressure is the force per unit area exerted on a surface by the weight of the air above that surface in the atmosphere of Earth, or that of another planet. Near the Earth's surface, there are more air molecules and therefore higher pressure. At high elevation, the decrease in air particles results in a decrease in the pressure. This is also shown on the graph to the left. Near the peak of Mount Denali, the number of air molecules is nearly half of what is found at 300 feet. That is why it's so difficult to breathe on very high mountain peaks. Air pressure is also connected to our work with rising and sinking air parcels that we played with in the lapse rate exercise. In the next lecture, we will talk more about air parcels. For this lecture, know that as an air parcel sinks, the atmospheric pressure increases, and the opposite for rising air parcels. The result is a decrease in the pressure. Another connection between moving air parcels and pressure is shown in this model. Note that cold air, say in the evening, sinks, resulting in a depression of the 500 millibar height, or isobar. The air is bunching up, and the pressure is increasing at the surface because of this cooling. On the other hand, air that is warm during the day rises, leaving a low pressure area, and an increase in the elevation of the 500 millibar height. Let's continue to play with this concept and move towards a model that explains air movement around different pressure centers, or air parcels. This model shows that for low pressure areas, surface winds will rotate in an anti-clockwise rotation, whereas for high pressure areas, wind rotation is in a clockwise direction. This concept is emphasized with these two images. The one on the left shows the opposite rotation senses for regional scale low and high pressure systems. The model on the right shows that for lows, as the warm air rises, surface winds move to fill the space, rotating in a counterclockwise direction. For high pressure areas, descending air, which heats while it compresses, pushes air away from the area, producing a clockwise directional flow. Now, the direction of these winds is in part related to the Coriolis effect, where things move to the right in the northern hemisphere and to the left in the southern hemisphere, as well as the surface friction. And one more time with some three-dimensional perspectives. In this model, we add the terminology anticyclonic flow for clockwise flow around a high pressure area, and cyclonic flow for anti-clockwise flow around a low pressure area. Note that in the upper levels of the atmosphere, air moves away from the low pressure area, which is called divergence, and towards the high pressure area, which is labeled as convergent airflow. Now let's start looking at weather maps, where pressure contours are used to represent the three-dimensional natures of air parcels. Isobars are lines of equal air pressure. So for this line here, anywhere along that line the air pressure would be 1024 millibars, and for this small line or contour around the low, the pressure would be 980 millibars. So what does it mean to be low pressure and high pressure? Well, that's explained in this part of the diagram over here. High pressure and low pressure are defined relative to the mean sea level pressure, which is 1013.25 millibars or 29.92 inches of mercury. Any pressure that's above that value is referred to as high pressure. Any pressure that's below that value is referred to as low pressure. So over here we have this high pressure system over the southeast, and this contour is the value of 1038, so it's high pressure. We have this prominent and very steep low over here northwest of Washington and Oregon, and the pressure is 980 degrees, which is lower than the mean value. Now we can use the location of highs and lows to infer both the direction and the relative magnitude of wind. If you are familiar with topographic maps, you may have realized that pressure contour maps are analogous to topographic maps. Topographic contours show the three-dimensional structure of the land surface, whereas pressure contour maps pertain to the three-dimensional pressure surface. And like these, there are various types of landforms, such as valleys, ridges, hills, mountains, etc. There are also similar features for pressure surface. We will concentrate only on two: high pressure ridges and low pressure troughs. The model on the top shows a high pressure hill over Tulsa. Here the weather is nice, sunny, and likely warm and dry. Note that the wind directions are clockwise around the high pressure zone. When we go down the pressure hill towards Chicago, we enter a low pressure trough where the weather is more inclement and the wind direction is counterclockwise. The two bottom images show examples of high pressure ridges here, and low pressure troughs here and here. These topographic elements help to define the shape of pressure surfaces and sometimes have important implications for the duration of weather events. This slide, for example, the reason for the prolonged drought in California is a strong high pressure ridge that is directing moisture and storms to the north. Oregon has seen some impact of this as well, as the weather has been a bit drier than usual, although not as dry as California. Weather folks are referring to this ridge as the ridiculous resilient ridge due to the long-term stability. This is bad news for California because due to the lack of rain, reservoirs are very low, and since mountains have not seen a lot of snow, the prospect for filling reservoirs with snowmelt is near zero. But the impact of the drought does not stop here. This slide shows a series of 9 maps of California. The top map shows the state of drought. The range is from exceptional drought in dark brown to abnormally dry in yellow. The other maps show the area where nuts, vegetables, and fruit are grown and the percentage of U.S. supplies. It's not hard to see that the U.S. relies a lot on food grown in California. And with a severe drought, it is likely that the production of these vegetables, fruit, and nuts will be impacted. And we can likely see that reflected in our grocery bills. Now, I have not talked about how to contour these maps. If you are more interested in contouring isobars, please see this video. A link is on the Blackboard site. As mentioned previously, Isobar contour maps can also be used to estimate the direction and strength of winds. There are two fundamentals. Winds move downhill from high pressure to low pressure. And the second principle is that the closer the contour lines, the steeper the gradient and the more powerful the winds. This diagram shows two arrows which are at 90 degrees to the contour lines. There's a shallow gradient and relatively weak winds around the high pressure area. Near the Mississippi, the gradient steepens and the winds become stronger into the lower pressure area. The final concept you'll need to complete the first exercise is knowledge of weather map symbols, shown here in this diagram. Much of this information is from the JetStream website, and you can get a lot more details from there. The striking thing about these symbols is the immense amount of information crammed into a very small space. I count at least 12 different variables or 12 different types of data associated with this symbol. For the air pressure and wind exercises, you will have to interpret the wind portion, both speed and direction, of the symbols. For example, there are two components. The ornamentation at the end refers to the wind velocity or speed, and the direction of the long barb indicates which way the wind is blowing from. For example, two barbs at the end of the long line indicates speeds of 21 to 25 miles per hour. As mentioned before, the line that starts from the location circle shows the direction the wind's blowing from. For instance, with this example, the wind is blowing from the north-northwest. From this example, the wind is blowing from the northeast. And from this example, the wind is blowing from the south. Here's an example of one of the weather maps from your exercise. I hope you're ready to tackle some of these problems. You'll be interpreting these weather maps and some other maps that contain weather symbols. Good luck, and please ask for help if you have questions.